Well, this is a quick demonstration of how we can use a shortcut by using proportions to solve a problem involving a force on a charged particle. The diagram here shows the setup where we've got three charged particles, two positive indicated by red and one negative indicated by blue, and their relative charges are shown. Rather than giving a certain number of coulombs, which is usually a little unrealistic because a coulomb itself is such a huge amount of charge, we just indicate relative charges, especially on a proportion type of question. And we're given the distance between the farthest most particles. And the question here we might ask is, where would we put the negative particle so that it is in electrostatic equilibrium? Now it's important to remember that in physics, equilibrium means that the net force on the object must be zero. And as you can see, because it has a positive particle on its left, then it's going to have a force on it of attraction, because unlike charges will attract each other. So we can maybe indicate that with a arrow like that. And so to be in electrostatic equilibrium, we need to have the same amount of force from the rightmost particle also pulling on it. So where must those be in order to have those two forces equal? Well, down at the bottom I put a symbolic form of Coulomb's law that shows the proportion, which is the force is directly proportional to each charge and inversely proportional to the square of the distance separating those charges. So I like to just think of this in two parts. The one part that's given is the relative size of the charge. So by virtue of the rightmost charge being 4 times as much as the leftmost charge, then it would have a tendency to exert 4 times more force. That's if the distances separating them were equal. So now we have to think, well, how can we change the distance between the particles to make up for 4 times as much charge? And because we have an inverse square relationship, we need to see that we need to have the leftmost charge be closer so that it can make up for its lack of charge. So how much closer? Well, if it were a straight inverse relationship, it would have to be 4 times closer. But because of its inverse square relationship, it just needs to be twice as close. I like to sometimes say it that the distance contributes more to the force because it has a square in the relationship. So what that means is I need to bring the middle charge twice as close to the left charge as it is to the right charge. Now if we have 12 centimeters to work with, and I chose that just for convenience, that means those two distances need to add up to 12, but the one on the left needs to be half the one on the right. And so the two sets of numbers that would work here are 4 centimeters and 8 centimeters. And so now, if we can kind of think of the end result here, the larger charge on the right is exerting 4 times as much force, but because it's twice as far away, that 4 times as much force gets negated by 1/4 of the force, and so we end up with both of those forces being equal.